Good morning. I want to thank everyone for joining us today in this webinar for phosphorus removal. My name is CJ Strain. I'm a professional chemical engineer, and I'm the Chief Technical Officer for Blue Water Technologies. With me as my guest today is Maureen Neville, an engineer with CDM Smith. Ms. Neville earned a BS in Civil Engineering from the University of Notre Dame. She's a 12-year veteran in wastewater plant design. She has applied her expertise in biological nutrient removal processes, add-on phosphorus removal processes, and aeration systems while serving as a lead process designer for the following facilities in Massachusetts: Upper Blackstone Water Pollution Control District, Marlborough Westerly, Marlborough Easterly, and the Charles River Pollution Control District, all wastewater treatment facilities. Maureen, you were going to share with us some engineering insights, is that correct?
Yes, I hope so.
Can you begin by describing your personal motivations behind the projects in your biography?
Sure. The ones that I highlighted specifically are the ones that I worked on, which were nutrient removal upgrades, where I did the work from planning level through final design. And each of those facilities had different nutrient limits, different challenges that they had to face. And what I really enjoyed about each of them was actually coming up with the optimal solution for each plant. It wasn't always a one-size-fits-all solution for all of them, and it's for me very interesting in trying to evaluate and determine what the best solution is. And in general, in terms of the work that I do, I always wanted a career I think that serves others, and when I focus on the outcomes of what I do see that tangible benefit, both in the receiving waters and the environment, and then the communities that are served by those natural resources.
I was recently at the NWEA show where Jane Madden, a VP for CDM Smith, was discussing reuse, recycle, and nutrient topics and thinking beyond the mold of conventional waste disposal ideology. How do your personal motivations tie into CDM Smith's culture in that regard?
I do think, as a company, CDM Smith, we try to not only find, good solutions for our clients, but also sustainable solutions. And I think, especially when we get into nutrient removal and we start to talk about the resources that are required to achieve some of these permit limits, for me, I always make sure I keep it in mind when I'm doing evaluations, starting back at the preliminary design level, making sure that you're considering the resources that are going to be used for the process and trying to minimize the impact that we'll have on the environment. So I think, as a company, we're always trying to keep that in mind, finding sustainable solutions for wastewater facilities and the ones that have maybe lower impact on the overall environment.
Yeah, and I think going forward, a lot of that work is going to become more and more important to secure funding for some of these large projects. I've heard that buzz certainly at a lot of conferences, and I think that's something that the industry is definitely going to see. As we proceed here through the webinar, I want to make sure that everybody knows that that we're going to provide PDHs at the end of this this webinar. For those who need PDHs, you can email. There will be a contact phone number and email on the screen. So if you want to get PDHs for attending, if you're attending in a group, I do need a meeting organizer to provide all the names of folks who need PDHs. But certainly contact us if you want to get PDHs for attending and being attentive during this webinar. Maureen first met Blue Water on this plant upgrade project in New England. Maureen, can you share a little background on this project, which is Westerly, Massachusetts, or in Marlborough, Massachusetts?
Sure. It's the Marlborough Westerly facility in Marlborough, Massachusetts, and the city actually does have two plants, but we're going to focus on the Westerly one. And Marlborough plants discharge into the Assabet River, and all the way back in '98, the river was actually classified as impaired. So at that point, Mass ET had informed 6 communities which had 4 treatment plants along the Assabet to start preparing for low total phosphorus limits. And they recommended that each of them start a comprehensive wastewater management plan. And that CWMP was to look at long-term wastewater needs, options for phosphorus removal to achieve the low limit they were proposing, and then also, what I&I removal or water conservation measures might plants be able to do, and then any other alternatives, say decentralization, if that was appealing or cost-effective. And so back in '99, these 6 communities came together and formed a consortium so that they could look at this issue on a regional basis, and that each facility, each plant, they might come up with their own solutions. Everyone's looking at it at the same time. They could stay on the same schedule. And now, 15 years later, all 4 of those plants are achieving a 0.1 milligram per liter total phosphorus limit, which was established based on the TMDL that was done. In terms of Marlboro Westerly in particular, their CWMP was completed back in 2007, and in that report, we did do some initial evaluations for phosphorus removal technologies, as well as baseline evaluations for improvements. And then we started preliminary design in 2008, and it was during that time frame, during preliminary design, where we really focused on final selection of phosphorus removal technology. We actually performed a side-by-side pilot with 3 different technologies, and it was out of that Blue Pro became the selected technology for Marlboro Westerly. And then in terms of completing the project life cycle, construction ended up being completed in 2012. So since 2012, Marlboro Westerly has been achieving less than 0.1 milligrams per liter total phosphorus on a regular basis. And in general, in talking with the operations staff, they have been happy with the Blue Pro process in terms of its performance, and then in terms of the level of maintenance and monitoring that's required.
I think there's going to be a lot of interest in how, in discussing the life cycle, how engineers interface with the permit writers. In fact, I just noticed a question came in that regard. We will be answering questions at the end of the webinar, so if you do have questions, feel free to type them into the GoToWebinar interface pane, and we'll definitely address those questions, especially that one in particular, at the end of this webinar. I do want to continue here, and Maureen, with the low phosphorus challenges in mind, what engineering principles and procedures were applied early on for technology selection? You mentioned piloting, of course.
Yes, and when we started looking at the different technologies, we had a whole list of non-cost measures, and then obviously costs that we had to look at in terms of making the selection. And when we were looking at non-cost measures, we were looking at ease of maintenance, prior experience, reliability, and ability to adapt to changing influent loads and flows, obviously the ability to meet the permit limit itself, and then some issues such as chemical usage, power usage, all of those factoring in to some of the non-cost factors, and then also power and chemical factoring into overall O&M costs for the 20-year planning period. And then wanted to look at footprint and again the impact of that on cost. So kind of holistically looking at the different alternatives, and having done a pilot, it actually helped with that because we felt like we were able to get solid numbers on what chemical usage was, what power usage was, and confirming that you can meet the permit that we're trying to meet.
And that's been a really huge, power requirements, life cycle costs. That's been a huge thing going forward in other New England projects that we've, participated in. We just finished up a project in Burrillville, Rhode Island, actually, that is going to be a Blue Pro system where, it came down basically to chemical and life cycle costs on what equipment would be selected, and really on what layer or level of multi-barrier approach, so to speak, to prohibit peak discharges of phosphorus or copper in that case as well is also on their permit from hitting the environment. So I think those are all really important selection criteria early on to identifying the project. Now, this westerly project, along with other Assabet River projects, really pushed the envelope in New England at the time for phosphorus removal. Now, you and I discussed the pressure to succeed, of course, and the commitment to the requirements of the end user. How big of a role did the process guarantee play in the equipment selection?
In this case, it was a very big role. I mean, there certainly were differences in some of those non-cost factors, and then even in some of the life cycle costs. In this case, Blue Pro was actually the least expensive overall, but the big seller for us was Blue Water's willingness to agree to the guarantees that we had requested. Their willingness to stand behind the product, their willingness to stand behind the treatment that they were supposed to achieve, and especially, maybe some of the technologies might have been a little bit more established, but treating to this level really, we're getting close to the limit of technology. And at the time, I think Blue Water might not have had quite as much experience. So, having Blue Water sign on and agreeing to 3 years of achieving, performance, which included power and chemical usage, was definitely a big selling point and made us feel much more comfortable with the selection, and it made the client feel more comfortable as well.
Okay. Well, we'll come back to the westerly plant in a few minutes, but with that conversation in mind, let's look at some of the dynamics of the industry across the U.S. I think this broad perspective will help answer the question, why reactive filtration, which is the Blue Pro process. Since the late 20th century, there's been a strong push, across the U.S. for numeric nutrient criteria, all tying back to the Clean Water Act, of course. And several states are beginning to feel the strong effects of that push. State agencies, especially in Florida and Wisconsin, have reacted, as most engineers in the industry are aware. And the industry is starting to see project growth come in line with these newly established nutrient criteria. A good story on the phosphorus or the numeric nutrient standards in Florida, I would point to an article actually written, and the title is Numeric Nutrient Standards for Florida. It was by Scott McClellan for CDM Smith. It gives a really good summary of the history of how that process was applied in Florida, how those nutrient standards were developed, and how the stories of the litigation and how the state finally selected and has started to implement those numeric standards. So you'll see similar stories like that, like in Wisconsin. I encourage everybody to become familiar with that because it's kind of a roadmap for states who have not yet developed those criteria. And I highlight these states, but that's not to say that there haven't already been several water systems designated as impacted and environmentally sensitive. Everyone is familiar with the Chesapeake Bay region, where nitrogen has been a strong focus, but P has also been regulated there. Blue Water has several installations in that region for phosphorus down to less than 0.3, less than 0.1 ppm. Other regions that would be familiar to audience members include nutrients in general, but the one that comes to mind is the Cahaba River Basin in Alabama and the Mississippi River Basin, impacting multiple states, where we're seeing drivers for even as low as 0.05 ppm or lower. Now, of course, one thing that we might cover in the Q&A is what's realistic in some of these nutrient standards. What becomes an economic or environmental burden versus an environmental saver regarding selecting a nutrient limitation. But there's numerous water systems throughout the western U.S. that have also seen stringent P standards as well. So we'll highlight some of those through the case histories that we have to share today regarding effective phosphorus treatment. We have a few of those for phosphorus limits in the range that we've been discussing, less than 0.1 milligrams per liter. But we also have some of the lowest enforced phosphorus permit levels in the world in the western U.S. The lowest actually installed and operating for a few years now is a 0.05, and there's a couple in the central U.S. that are looking at a .022. So to my knowledge, those would be some of the lowest enforced in the world, and we'll talk about those as we move forward. I want to begin by defining reactive filtration because, again, that's the question. Why reactive filtration? Reactive filtration, the Blue Pro system, is an adsorptive process. It's different than conventional methods. And when I talk about conventional methods, I often say that they're diffusion limited. So what do I mean when I say diffusion limited? The process of adsorption, actually, let me go back to a couple definitions. Absorption versus adsorption. The process of absorption with a B is one in which a fluid permeates or dissolves, or is dissolved by a liquid or solid. For example, water can absorb gases. A sponge can absorb water. Absorption involves the whole volume of material. Whereas adsorption, this idea that we use for reactive filtration, adsorption is a surface-based process. Adsorption with a D is the adhesion of ions and species from a fluid onto a surface. So when speaking of phosphorus as our fluid in water, as our fluid of water, the process creates a film of phosphorus on the surface of a substrate, which is our Blue Pro coated media, our reactive filter. So we'll, and we've all seen adsorptive systems actually and interacted with them. Adsorption systems and other applications, there's a few examples such as activated carbon filters, silica gels, zeolite catalysts. These all come to mind as systems that utilize adsorption. Now, people familiar with these adsorbents will also appreciate my next point. Blue water utilizes a continuous backwash filter so that there's no chance of media exhaustion. The Blue Pro process is a genius twist, so to speak, on simple systems so that a disposable adsorptive coating is generated, stripped, and continuously regenerated in a 4 to 8 hour life cycle. So those who have worked with adsorptive filters before know that you have a certain loading that you can apply before you have to replace the media. So that's true of carbon filters, zeolite catalysts, or you need to recharge the media in some complex process. The beauty of the Blue Pro process and why it uses a continuous backwashing platform is that we can apply a surface coating to the media in process, and that coating is stripped and regenerated. And I'll describe how that process happens. But basically, this isn't your grandfather's filter for those who have seen continuous backwash filters in the industry. It's marrying some very simple steps and techniques together, but it gives a very complex and a very genius system for adsorbing not only phosphorus but a variety of contaminants. And we'll be, again, giving details on the process and talking about this as we talk about the installations and case histories. Now, I mentioned that the Blue Pro process is a bit of a genius twist on simple systems. These continuous backwash vessels that Blue Water specifically designs and optimizes geometrically facilitate the Blue Pro adsorptive process with these regenerative media surfaces. We use fully modeled 3D CAD systems before production even begins, which mitigates a lot of the common fit issues through construction and commissioning project phases. Now, these systems are branded as a CentraFlow continuous backwash filter that we use to integrate the Blue Pro process. And the beauty of these systems are that they're very efficient systems that use gravity and a low-energy airlift pump to cycle the media. So the media is continuously recycled or circulated, but there are no moving parts. This ultimately means a low life cycle cost of ownership. And those familiar with these media filters know that they do produce a very high reuse quality filtration. In fact, they're approved and used throughout many states for that purpose. They're California Title 22 accepted, for example. So the fact that there aren't any moving parts and that they produce a very high quality of water, they're very simple and have a very low energy input, makes them very amenable to implementation with the Blue Pro process. So my next slide here, I'm going to pause briefly for a video that talks through the flow through a continuous backwash filter implementing the Blue Pro process. So you have your dirty water coming in, your typically clarified secondary effluent comes in. There is chemical added directly into the media to form that coating, and the water flows upward through this reaction zone of the bed. And the water flows over a fixed effluent weir at the top. Now the media is recycled using the central assembly. You saw the wash box highlighted. It flows downward by gravity to the central cone where the media is collected by an airlift pump. Now this airlift pump provides a scouring energy 10 times that applied to static media filters. So basically what that means is that old adsorptive surface is completely abraded and removed. So we never get to the exhaustion point for that surface loading of that media. So that old coating is completely abraded to remove all of your phosphorus, all of your contaminants go out with the continuous reject stream here, and a clean media returns to the top of the bed to receive a new coating and to absorb additional phosphorus from the influent stream. So that's basically the cycle through the process, and we'll focus in again on some of the properties of adsorption as we continue through our presentation. So here, again, adsorption is a surface phenomenon. So I have a few pictures and graphics here that illustrate that. When I said, this process doesn't use your grandfather's filter, maybe going back to that might illustrate that a little further. In conventional coagulation filtration processes, you would have mixed tanks, you would have flocculation tanks where you're trying to form a large particle size in the water that can be physically removed by a media filter. And there's a few things that are limiting that entire process as far as efficiency. One is you're throwing chemical into a big basin, a big bath, where if you're trying to get lower and lower phosphorus, to keep your probability of contact between your phosphorus and what you're adding, your chemical, to keep that probability of collision and reaction up, you have to add more chemical the lower and lower that phosphorus concentration goes. So that's one thing. It's not an efficient way of using chemical. All of the removal, uptake of phosphorus happens within that flocculation chamber. And then it's subsequently physically removed by a barrier downstream. And that brings us to the other issue, is that physical barrier downstream, since we're purposely building large particles, is we're purposely operating that filter in a semi-plugged state. So again, this is conventional coagulation filtration, and operating the system in a semi-plugged state is obviously going to lead to reliability issues such as plugging, and it's not a sustainable way to remove phosphorus, especially to these low levels. So again, that's conventional coagulation filtration. When we're talking about the Blue Pro system, again, this is all surface. This is a surface phenomenon. So we're coating the media, which you see here. I actually have a couple of pictures from a scanning electron microscope. This is just a close-up of a media granule, and it's just a commodity silica media that has an affinity for a hydrospheric oxide coating. So we apply our chemical addition directly into the filter bed so that we get this coating on the media, and that's a process, again, that is very amenable to providing a very high surface area for that water to trickle over. So again, the surface phenomenon its efficiency is directly tied to how much surface area there is. So with this massive surface area of the bed, we get great uptake of phosphorus. And since we're not focused on creating large particles prior to the system, we get a free flow through the media, which lends itself to a very reliable process, a very sustainable process for removing phosphorus. Another thing that I like to highlight, because simulation work is often part of the selection process early on, is this process is very simple to simulate. We can simulate it on the bench scale, which we've done for many of our projects, not only our municipal nutrient removal processes, but also for industrial processes where we're looking at metal hydroxides, removal of trace metals such as copper, zinc, mercury, or lead. So we can bench scale that in our laboratory. We have some fairly unique and proprietary equipment for simulating that process. We can also bench or pilot scale this very simply. You see pictured here a 50-foot trailer that has all the systems on there for nutrient removal. It can be set up within a day, operated for a couple of weeks to collect representative data for the plant modeling and design, and then it can be decommissioned within a couple of days and removed from site. So it's a very mobile and actually a very clean way of modeling a process up front and using it as a tool for equipment selection. So Blue Water's modeling, through pilot scale, through installations, etc., is pretty important. Again, in early equipment selection. Another thing that we like to highlight and focus on is a whole plant approach to phosphorus removal. With our Blue Pro system, we really focus on being able to incorporate an internal recycle to the system. Now, this is very intuitive, I would say, to a process engineer who's used to increasing efficiency of a separation process or a chemical extraction or adsorptive process with internal recycles like this. So we're adding chemical, we want to get more efficiency out of it, and this internal recycle actually helps a lot. So within this very simple process flow diagram in a plant, you can see the Blue Pro filter installed and integrated immediately after the secondary clarifier. The rejects from that process, which represents roughly 4 to 7% of the forward flow, the rejects are very rich in all of the removed hydrospheric oxide coating. It also has the phosphorus in it as well. So the residual reactivity to that it can be incorporated in this recycle loop as you would a conventional settling chemical addition process where you're precipitating the phosphorus out, settling it in secondary clarifier. So you get that increased chemical efficiency that way. Blue Water's modeling has shown that the adsorbate loading on the hydrospheric oxide within the Blue Pro filter itself is only roughly 40 to 60% of its capacity in most municipal installations. So that leaves a significant amount of reactivity that comes back around to the front end of the plant. In fact, Westerly Marlboro uses this configuration now, especially to hit their winter level. I have some data to share in that regard where I'll comment a little bit more on this. But ultimately, this recycle, this whole plant approach and planning allows us to hit reliably those 0.1 limits and less than 0.1 with the Blue Pro process while really minimizing our chemical input. So we're back to the Westerly project here. Let's return to a little bit of plant discussion and talk about some lessons learned regarding phosphorus speciation. I want to begin with this. This plant had very high levels of recalcitrant P, phosphorus, that represented treatment challenges. So I'm going to let Maureen share some insights in that regard.
Sure, thanks, CJ. This was the first facility where personally I had encountered an elevated baseline level of recalcitrant phosphorus. And recalcitrant phosphorus, can be defined as that portion of soluble phosphorus that cannot be removed by a conventional treatment technology. So it will pass through the plant untreated. And it comprises the soluble, acid hydrolyzable, and organic fractions of the phosphorus. And when you start to look at maybe typical concentrations, you might be in a 0.02 milligram per liter or less. And at Marlboro, it was actually discovered during the side-by-side pilots. We were actually seeing levels sometimes over 0.4. So if you're seeing this baseline level of 0.4 that can't be treated, obviously at times you could have issues achieving a 0.1 limit. And so we tried to actually, maybe try to identify what the source of it was. but it became very difficult. Industries that we had maybe thought could be responsible, we couldn't actually ever track it. So it's just something that Marlboro Westerly plant has to continue to deal with. And if you look at the data on the screen there, you can see that even in January through February and then all the way through the low phosphorus limit, basically the plant is trying to achieve as low as possible. Basically remove all the reactive phosphorus that they can, so that when they get these periodic spikes of recalcitrant, it will be averaged out by the remainder of the data.
Yeah, in just in that regard, going back to the performance test back when the plant was commissioned, the goal in the stated performance test was to maintain actually a 0.07 throughout the performance period of 30 days. But it was also stated, again with that whole plant approach, that various parties had responsibility for meeting phosphorus limits throughout the plant before the Blue Pro system had to take it down to this 0.07. So over a 30-day period, there were times when that recalcitrant phosphorus would come up and wouldn't be removed throughout the rest of the plant. And so, with the way that the guarantee was written, those weren't included in the average. But so you can see that chart here where the Blue Pro system maintained roughly an average of 0.04 total phosphorus, and as Maureen alluded to, throughout the entire time, all of the reactive phosphorus is removed. And so you translate those observations to the data set that's been collected over the past couple of years. It's very simple for the plant to remove down to below a 0.04 level throughout the winter time, to maintain close to that 0.01 level, plus or minus. They basically round to one significant figure for their summertime season, which they're able to meet that 0.1. But the recalcitrant phosphorus is definitely an issue. And there's been a lot of studies over the last 2 years, I'd say. The ones I'm most familiar with are out of the University of Washington in Seattle, Washington. And they've been looking at this phenomenon for a couple of years now, looking at plants that have all of the reactive phosphorus is gone, and they're looking at the recalcitrant phosphorus and its effects downstream. And basically what they're seeing is it's not really, that entire fraction is not completely biologically available, and therefore won't lead to the eutrophication issues that we sometimes see. I think in the future that might tie into how permits are written, or at least it should, because there's going to be a lot of science behind that argument in the future. So I think that's important to keep in mind as we go forward through, through some of these project discussions. It won't really come up in any of our other stories, but as you're going through the industry, as you're going through future projects, I think everybody is going to see this at one time or another in their career. Is there anything? Yeah, go ahead.
I was going to say, and just to add to that, I think that's another lesson we took away from this project, is that anytime we go to another facility and they have a low phosphorus limit, we always try to, up front do sampling to establish if they have, an elevated baseline, or if they have periodic issues with a recalcitrant P. Because as you said, we've had these discussions with the regulators before, but there isn't necessarily a lot of science, or hadn't been, on the bioavailability. So hopefully these studies that you talked about will kind of help influence the way permits are written, whether it's a reactive P or an ortho P rather than total. Or I think this also gets to how permit limits in general are set, because for here at Westerly, they have they have a 60-day rolling average permit from May to October. So they have, some, it's a little bit less lenient, or a little bit more lenient than, say, a 30-day max that some permits are in Massachusetts. But, I think they've been doing a lot of work on evaluating nutrient removal facilities. And, even at the high-performing plants, you are going to have some variable effluent performance. And so in addition to that, if you have this recalcitrant issue, achieving a monthly maximum, or a 60-day rolling average can be really, really challenging when permits are set that way.
Yeah, agreed. And I don't remember the author of the paper over the last couple. Oh, Bo Lee. is the graduates who's been working on this study. I believe she even presented it at WEFTEC last year. It's Bo Lee, B-O-L-I, Bo Lee, and she's presented a few papers in this regard. There's a lot of science behind it now, and it's continuing. They're doing a lot of different algae assays and arrays trying to grow up different things with recalcitrant phosphorus. So there will be at some point a lot of data to share with the industry, and I think that should definitely be leveraged and used to give the end user and really the end user, the taxpayers, and really the best solution to protect the receiving waters in every specific application. And I believe the professor on that one is Michael Brett as well. So if you want to see those papers, email me at the end of this presentation. We'll see if we can put you in contact or at least point you to a paper. Now, over the next few slides, I'm going to share some data sets that will highlight some of the design considerations that we've discussed, and primarily and give you a little history on this process as well, because as Maureen mentioned, at the time that we did Marlboro, we didn't have a whole lot of installations of this technology, the Blue Pro process. Now we have a few dozens. The Blue Pro process was really the core that Blue Water used as when Blue Water came to be a company. It was founded around this process of adsorbing phosphorus. And since then, we've added other product lines and built ourselves up within the industry. But our first installation for Blue Pro actually came in 2005. So we've been implementing this process at full scale for about 10 years now. So there is some really nice data sets out there. And we learned a few things on our first installation regarding the internal recycle effect that we had discussed a couple of slides ago. This is from our first plant in Hayden, Idaho. The thing I want to point out is this is a very conventional activated sludge plant. It's got secondary clarification, chlorine disinfection, then it discharges. During periods of the year, it's reusing and irrigating a farm. Other periods of the year, it's going to a river as the receiving waters. But you see that they have no phosphorus removal systems implemented in their secondary system. Their secondary clarifiers bounce around from 4 to 5 milligrams per liter. When the Blue Pro system came online, and it was a two-stage system that was installed, you see an initial drop right away of 90% through that filter, that first stage, and then through the second stage you see another 90%-ish drop. But then you see that effect of that internal recycle in the plant, bringing the rejects from the Blue Pro back around with their remaining reactivity to that chemistry, that hydrospheric oxide coating that's been scrubbed. And that basically will remove a significant amount of phosphorus through you can do it in the primary system and through the secondary system, whatever each individual plant makes the most sense. But you can see here that it lowered the secondary level from roughly 4.5 to averaging, jumping around 1. And when you can do that up front, it's very simple for the Blue Pro system to polish to extremely low levels. In this case, this particular plant, I have some data sets here. This is looking at the effluents from the first and second stage over a 3-month period back in 2005 and 6. And basically what you see is that first stage is very effective at removing phosphorus to less than 0.1, which is a level that we're talking about today in single-stage systems. Now, in various parts of the country where we're talking about extremely low levels, less than 0.05, less than 0.02, we basically demonstrate the limit of technology. This, again, is a very highly tuned adsorptive process. This shows over a 3-month period or 2-month period phosphorus removal in a second stage that averages less than 0.02. And I'm here today to tell you that is a perfectly tuned system. There's no process upsets in there. That's something that I want to point out because, again, I view this data set as a demonstration of the limit of technology. and it's difficult and costly to get here, but it can be done. We do have installed systems that are permitted at less than 0.05. But again, this is a little history. This is the first Blue Pro system that Blue Water installed. The modeling protocol was actually written by C.H. Duham Hill, and then this data set was subsequently collected. Some highlights from the modeling of this plant after startup: it averaged less than a 0.02 milligram per liter P, as I mentioned, over a multi-month period. 1 month average is pretty dang low, again illustrating the limit of technology and getting all of the reactive P. So again, if we had recalcitrant P in this stream, we would have want to know that up front. Another story that I want to share with you, just to keep moving through a couple of these for you, is a recent installation in Arkansas. Now, everything that I'm sharing from this point on is 2013 or 2014 startup. So this one was recently started up in Lincoln, Arkansas. It's a smaller plant. They peak at 2.3 MGD, but they do have a deliverable of that 0.1 milligram per liter phosphorus that we discussed. You can see here from the performance test when it was first started up, this particular project had a 1-week performance test. So you can see it here. Their deliverable of 0.1 was easily met. And again, this is a single stage system. So obviously they don't have issues with recalcitrant P here. And the system is very effective for removing the reactive P that they do have. It's also that last one was also a good example of an above ground individual tank installation. Marlboro, we went in concrete with multiple filters per cell, multiple filter modules per cell, and this one is another example of a concrete installation where you have filters. Actually, these are individual cells, but this is a 2-stage system. So a little different story to this project. This is in Grangeville, Idaho. Like the Marlboro project, it started a few years ago with a pilot demonstration. And that pilot demonstration was the only one the plant did. It was successful in meeting their deliverable of less than 0.067, so they did have a fairly low deliverable for total phosphorus. They didn't want to make any adjustments to their plant upstream either, so their secondary process had kind of an older, outdated clarifier that they haven't upgraded yet. And so they didn't want to mess with it. So their entire phosphorus control upgrade, so to speak, was in adding this tertiary system. That's why they went with a 2-stage system. And so that, with the internal recycle and everything, provides an extremely well-performing system. They actually averaged less than, or averaged a 0.02 milligram per liter total phos in their startup performance period, and had lows of 0.01. Reactive phosphorus was completely gone. And it's interesting to note that this was during a spring melt event, so they had infiltration that raised their TSS to over 100 milligrams per liter coming into this system out of the secondary. So this performance was maintained during a worst-case scenario. They were overloaded hydraulically, and they had very high TSS. But again, we passed the performance test, so they were very, very pleased with the system. This next case that I want to share with you is one that illustrates some of the ancillary benefits of the Blue Pro process. I've highlighted and described how it absorbs phosphorus as a surface mechanism for removing very high efficiency. It will also absorb a variety of metal hydroxides. So I mentioned Burrillville, Rhode Island, which is a current project for us that's in design. They, in addition to having a 0.1 on their phosphorus, they have a very low limit on their copper as well to meet. We have several other projects that have been operating throughout the U.S. We have a Colorado project that has zinc and cadmium in addition to phosphorus. We're commissioning a project in Montana that has lead and copper in addition to their phosphorus. So there's a few of these stories around, and we're actually one of the pioneers also with removing mercury. So this was one project that was piloted back in 2010. You can see our pilot system was brought to the site. The system was demonstrated and modeled, and then we went into design and we're installing. It was installed last year. It'll be commissioned this year in 2014. So another medium-sized plant peaking at roughly 5 mgd, but with some fairly stringent requirements, not specific to phosphorus, but to other elements within the water. Their phosphorus, I guess, considering what we've been talking about today, is relatively lenient. But that's another good showcase of what Blue Pro adsorptive processes are capable of. And a few more things that provide a value engineered approach to any project. When we're talking about this reactive filtration, adsorption versus coagulation, we've shown that we can achieve lower phosphorus because, again, you're relying on a surface area and that contact with the dissolved phosphorus that you can achieve versus the constraints of coagulation in a basin. So you can get lower phosphorus. You get higher efficiency because, again, your contact efficiency with the phosphorus is higher. So you use less chemical. And in addition to that, a lot of times using less chemical overall, less polymers, different things like that, you can get better dewatterability out of the system. So we've contrasted for a target of 0.1 some different usages using an adsorptive process versus a coagulation process at 1 mgd. And basically with an adsorptive process, these are fairly typical chemical usages. Your chemical is going to be, roughly half to achieve a 0.1 that you would use in a coagulation process if you can maintain this. You're going to generate less sludge because of that, and you're going to consume less alkalinity. And that's what we found out in several of our cases where we've installed is with using less chemical, some of the ancillary chemical expenses like alkalinity addition and things like that are reduced or eliminated as well. That becomes expensive if you're trying to do lower level phosphorus removal with a coagulation filtration process. And one last story to share with you is related to changing permits, future needs, and the flexibility that this platform, the Blue Pro platform, can provide to a customer today. So if, and we've seen this throughout the New England area, we're just considering the number of plants that have begun with a single low-level nutrient requirement, and they've gone to more stringent requirements for both P and N. This treatment platform provides a sustainable tool for future flexibility and really meeting those future needs. So we have systems that are installed for both phosphorus, where they've had a phosphorus limit for several years now, and they're now starting to get nitrate permits. And we've also seen the reverse as well. This is one example of an AECOM project that was designed and built and has been running since 2009, where they had both a fairly stringent nitrogen, total nitrogen as well, permit level, as well as a lower phosphorus of 0.3. And Maureen, where have you seen similar scenarios like this in the New England area?
Well, we've seen it in specific watersheds. I mean, I think for Massachusetts and other areas in New England, we continue to see the permits evolve and limits decrease because I think regulators are still trying to develop the guidelines for strategies on how to set the permits, because a lot of our plants are influenced by downstream waterways, whether it's the Narragansett Bay or the Long Island Sound, and so exactly which permits to settle in on is kind of developed over some time, and we do have a couple clients where they went through millions of dollars, tens of millions of dollars of upgrades, and then basically as they're completing them, they start to get a lower permit limit or a lower nutrient limit. So I do see the benefit of having a system which has the flexibility to achieve both phosphorus and nitrogen removal.
Mm-hmm. And just as an added comment, it's not always a you have to look at your loading with a biological denitrification system as well. And that's something I want to be clear about as the equipment provider is sometimes you do have to expand the footprint to provide that detention time that you need for that biological growth rate. Now, that's not always the case. Quite often, this is at the back end of a plant that does a pretty good job at removing nitrates. Maybe they are already a BNR that's going less than 10 or something like that. And so they're only having to polish a few more nitrates. So that can sometimes be done in an existing system as is with hydraulic detention time available. Sometimes in other scenarios, though, an expansion of the filter system to provide that a slightly lower hydraulic loading rate is a requirement. But that's basically the end of our stories today. Again, just to recap, we've shared a lot of information about adsorptive efficiencies and reactive filtration. You know, this is not your grandfather's filter. This is a new approach to phosphorus removal systems that has been identified and proven to date. And it's a very simple system approach with barrier treatment. So both those ideas are very important. One, you have a barrier to TSS and phosphorus at the back end of the plant, and it's a very simple system that most people will understand, very easy to operate. It's low phosphorus capable, and just the intrinsic properties of this configuration lend itself to low chemical costs, or at least minimize chemical costs, and O&M efficiency regarding energy input and various considerations like that. And there's process synergy for future concerns, like trace metals, if they should be added to the permit, or nutrient changes as well. And I guess the bottom line for a lot of operators out there is it's a simple system, and it really is. So with that, we've wrapped up our webinar topics, and I want to start addressing the questions that have come in. And some of these, you know, I'm sure will be directed towards Maureen, and some of them will be directed to myself. I do just want to again remind you that if you want PDH certificates for this webinar, please feel free to email the address on the screen, or you know, feel free to call me at my office number as well. So we actually do have many questions, and we have about 5 minutes. So I'll try to get through as many as I can. So there's one for Maureen here that I'm going to direct to Maureen here. It's mentioned a 0.4 milligram per liter recalcitrant P, but a 0.04 is shown on screen, which is correct. So Maureen, do you want to address that? I'll go back to the screen, but I think I have an answer to that as well.
Yeah, I think when you're looking at that data, the 0.04 was the actual effluent when they didn't have recalcitrant issues. And so I think, CJ, as you pointed out, you know, we had told, in terms of the performance test, in our specification, we had defined what the baseline recalcitrant level would be, and I think we defined it as it wouldn't be any more than a 0.03 or a 0.04. And so on days when the recalcitrant level was above that limit that we set, then those days fell out of the data set for the performance test. Mm-hmm. So those days don't show up in the data on this graph because the influent that the plant was providing, the Blue Pro system, didn't meet the limits that we set in the specification. The 0.4 I mentioned is just on a day on another day when we've been doing sampling and analysis and we calculated it. They've had some days where it's been as high as 0.4.
Oh, okay. So that clarifies it for me as well. Because I thought when we were talking about 0.4, we may have been referring to some of the achieved levels during the winter operating period where they're a less than 1 permit. But okay. That's pretty amazing that it's as high as a 0.4, you know, that the right. Recalcitrant P would be up that high.
And that 0.4 was actually from the pilot. During the 2 weeks of piloting, it hit 0.4 on the last day.
Another question that I want to get out there just so that we keep moving through is I'm going to direct this to Maureen initially, and we'll let her respond to it. How are NPDES permit writers responding to optimization projects? What's your take on this?
Optimization projects in terms of improvements that people are trying to make in response to the permits. What do you think?
Yeah, I would think so. You know, some of the I would say with the pilots that are being performed throughout the industry, and a lot of that's public information now. How
Hmm.
do you think the permit writers are responding to those projects, reports, and weighing them as they consider their new permit content?
Yeah, I think it's so specific, region to region. We are working with one of our clients. We've been working with the regulators. This is one of the plants that had permits that we designed around and then got lower permits, and we are trying to, now kind of work through giving them some time to optimize the performance of the plant that we had designed and constructed. But it's been hard work to get to that point of, kind of allowing the plant to achieve what it can with the processes that it has before, ratcheting down the permit again. But I think, in terms of the way permits are being written and in terms of how much regulators are working together with plants, I think it's really very specific to a region. That's what I've seen.
Yeah, and I think that's there's a few questions in here that are going to be project specific. Another one that came through that is directed towards myself is do we have basically a residential size Blue Pro system available? And the short answer is no. We do have small community size Blue Pro systems available. I think the smallest that we've installed is about a 5-gallon per minute system. And it actually does have a low phosphorus requirement. It's a 0.06 milligram per liter phosphorus requirement. But once we get below about 5 gallons a minute, then it's probably not the most economic option. There might be small membrane systems or things like that. As a single residence, it becomes probably not very cost effective to go with, a complex control system plant approach. So I hope that answers your question. Another question that came through is, what are the total project costs? Now, I'm not sure. That's obviously going to be very specific for each project. And so I'm not really sure how to answer that. I don't know if, Maureen, do you have a round budget number for the Marlboro upgrade?
I do. The final construction cost, including change orders, was $27.5 million. Now, while that was a 5 MGD about on average plant, that included a lot of baseline improvements to the facility because it hadn't been upgraded in a while. So we estimate that about 22% of that 27.5 was directly associated with the phosphorus system.
Okay. Yeah, as you can see from the pictures from Carlin Contracting, which was the construction company for the project, you can see that the entire plant went through a pretty significant upgrade. I mean, from the aerial views, it doesn't look like there was hardly a part of the plant that wasn't touched.
There wasn't. It was pretty unbelievable when they were going through it all. So at Marlboro, it would have been about $6 million associated with the phosphorus removal system.
Okay. We have time for just a couple more questions because we have hit our hour mark, and I'm going to take two that are related to the biological nitrate removal, the Blue Night system. So there's a couple in this regard. One of them is just a clarification on that the nitrate removal happens within the same Blue Pro filter system, and yes, that is correct. So if there's a single stage of the Blue Pro installed, like several of these projects are single stage, that Blue Night system would be integrated within that same footprint within that same treatment stage. So this project here in Arkansas is a good example. It's a single stage, smaller system that they could easily add a control system to add supplemental carbon to do denitrification in the future if they needed to. And one last question also relating to biological denitrification, and that's biogrowth control within a system like this. And that biomass, that resident biomass is controlled by the airlift rate. So that's all tied into head loss within the filter and the control system that senses the effluent nitrate and different parameters like that. But basically the wasting rate of mature biomass is handled by the airlift that is integrated within the central assembly of a Blue Pro or Centraflow filter. So That is all the time that we have today. I wish we had a little bit more because there were a lot more questions. But I do want to thank everybody for joining us today for this webinar on phosphorus removal. I want to thank our guest, Maureen Neville, for taking time to participate. And again, I want to wish you all a good day. If there are any questions, requests for PDHs, please email the contacts on that last screen. And I'll get there real quick and leave it for a minute before we sign off. So again, thank you all and have a great day.
Thanks, CJ.
Bye.